Hi, in the present video I will show you that the Bohr-Sommerfeld rules can be derived directly from the formalism that we are developing up to now. Let's go to the derivation. This derivation will help us tackle a difficult problem in quantum mechanics related to the duality principle. So let's begin presenting the duality principle in terms of what we have already done. Indeed, we must try to understand the role of corpuscles or particles and waves in the realm of quantum mechanics. And this is the same with this formalism that we are developing up to now because we began with Liouville equation and thus with a joint probability distribution that is in principle related to particles and fields. And it's up to now, I will get back to this point later, related to ensembles. But in the course of our demonstrations, we have connected this probability density function with the probability amplitudes related to the function psi. And of course, we have found in the course of the demonstration the Schrödinger equation, which is, mathematically speaking, an equation related to waves in fields. We have then the issue that we have in this side, an equation which is certainly related to particles, and in the other side of the derivation, an equation which has the structure of a wave equation. How can we manage to connect these two situations? Of course, it's not possible to solve this issue at this point. We are just presenting it. We will have to develop our theory in general, not only the mathematics, but all the mathematics and the interpretations to show that we can, in fact, solve this apparently contradiction in usual terms without taking research to wave-particle duality. But at this point with of our developments, it is really an issue that may show itself very important. But to go into this issue, let us develop the mathematics related to the Bohr-Sommerfeld rules. Let us show that these rules are a direct consequence of the axioms. Okay, how can we show that? We have here, we can already write simply the Planck's constant here. We have one of our axioms written in terms of Fourier transform, taking on the joint probability density function, and this Fourier transform is taken into a product of two functions. And we know that if we have a Fourier transform that takes us into a product of functions, we must rewrite this function as a convolution. So the convolution that we must have, we can mathematically show that this is done in the paper, published paper, is this one. So this is the way we must write the joint probability function in terms of joint probability amplitudes, that is, amplitudes written in the phase space, to have this product written in the configuration space. Okay, but this will uh, have deep consequences in what that we will show in what follows. Now, if we write this, it's easy to show that this Fourier transform is taken into the product. This is the subject of the convolution theorem, can be written in terms of these two Fourier transform, the product of these two Fourier transform, which connects the probability amplitude in phase space to the probability amplitude in configuration space. That is, each one of these Fourier transform can be related to the projection of the psi into the configuration space. This is the realm of the derivation of the Bohr-Sommerfeld rules, as we will see just now. The consequences then that are that we can write, as we have shown previously, the probability the amplitudes in configuration space is related to probability amplitudes in phase space, as by means of a Fourier transform, that is, by means of this transform. Of course, we can take the complex conjugate. This will make appear a minus sign here and a conjugate here, but if we also make delta q negative, this sign is maintained. So the complex conjugate can be written this way if we take it in the negative infinitesimal displacement delta q. This is interesting. These two expressions are interesting because we can, at least in the informal terms, understand what is going on. Because we know that we can write, this is a result that comes with the derivation, we may write our momentum operator in these terms. If we at least formally substitute this expression in the exponential here, we get simply this exponential, because we simplify this minus IH bar here, and we get simply that. And since in this case we don't have a dependence here in P, this is not dependent on P, we can take it out of the integral, and then we may have just this result, which is using, let's use the Q, using this expression for P, exactly the psi displaced by this infinitesimal distance, because we know that this is the relation. And in fact, if we can write this relation, of course, because we can make simply delta q equal to 0 here, and then we immediately have this relation which justify our use of the delta Q here. Because we put this out of the integral, then the remaining integral is just psi. Okay, this is at least formally it is interesting to have these results. But we now have something very important related to this integral. Let's focus into this relation, which represents the way that we can, in some terms, drag our psi from a point Q to a point Q plus delta Q. This is what is meant here. Yeah? Point Q from a point Q plus delta Q by means of a transformation, a Fourier transform, that has a kernel given by this exponential. This is very important. So our kernel is given by this if we want to connect probability amplitude written in point Q of the configuration space to a probability density, amplitude written in a point Q plus delta Q, also in the configuration space. This is important because now we can try to understand which will be the transformation that we must use to take the psi in point Q to psi, the same psi, but in a point Q plus delta Q when this is not infinitesimal. This resembles a lot Feynman's calculations, calculations using Feynman integrals, path integrals, and what we have to do is to simply make successive integrations using this kernel and write this simply as this transformation when this kernel, where this kernel is just a product of these ones, taken, of course, successively in the points delta Q, 2 delta Q, delta 3 delta Q, etc. Since this kernel is expressed as an exponential, this product takes us into an explanation of a summation of Q taken in the successive points multiplied by delta Q, of course. And this, if we assume delta Q as infinitesimal, this means that we have to take to cover the distance, the finite distance, delta Q, a number of steps which goes to infinity. Of course, this expression that we get in the exponent of the exponential is just an integral, and we can write the kernel of the transformation, of the complete transformation for finite distance as this integral. This is completely equivalent to Feynman's approach, now taken on the phase space, but it's the same thing. In fact, this to be quite correct formally. This is not dp, but what Feynman is right as a big D, because it represents a succession of application of the kernel related to the infinitesimal displacement. But what is important here for us is this result, because this is what we will use to show the Bohr-Sommerfeld rules. In fact, this is the way now that we connect these two amplitudes. It's what we were trying to do, how we connect the psi amplitude in two different points. But this means that if we have symmetry, this is the point, this is the important point here. If we have symmetry, then we must have the psi on the configuration point q plus delta q exactly the same as psi in q, but with the freedom of the sign, because what we have to as an observed quantity is just ρ, which is the square of psi. So if this is true, and if we have that kernel connecting the two functions, the function psi in 2 points, we then must have this kernel as equal to minus or plus 1. But to have this kernel as this plus or minus 1, it means to have Bohr-Sommerfeld rules already generalized to half integral numbers. This is it's interesting that the process of derivation gives us not only integral numbers but also half integral numbers, and it is really commonly a drawback that is assigned to Bohr-Sommerfeld rules, because it, as the way we know them, they do not introduce half integral numbers. But now we can see that making this derivation path, we can indeed find these half integral numbers. But the most important thing here is, and this will be used in the next video to relate particles and waves in some sense, in the beginning of our discussion about that, is that the way we derived Bohr-Sommerfeld rules is by assuming that there is a symmetry in the process. This is important because this will have some important relations to semantic heritage. The semantic heritage that will come from here is related to the fact that now we have these, when we have symmetry, of course, we have this integral representing a discrete change in momentum, a discrete transfer of momentum in some experiments. This will help us, as we will see in the next video, interpret the wave-like phenomena in corpuscular terms only. And this will help us begin to solve the problem related to wave-particle duality. There is no duality here in this approach. But this will be done in the next video, when we will then tackle the problem of a corpuscular approach to wave-like experiments. Thanks for watching.